What if a comet out there was alive? Right now, in the freezing dark beyond the sun, a traveler named 3A Atlas is exhaling 40 kilograms of water every second. That's not supposed to happen, not out there. Astronomers are whispering. It's breathing, but this isn't just another comet story. Inside it, nickel without iron, cyanide in its tail, and signs it may be older than our entire solar system. And just as scientists focus on this visitor, citizen astronomers stumble upon the largest odd radio circles ever recorded. Meanwhile, Mercury and Ceres align over the October skies. The same week, Blue Origin's mission raises more questions than answers. Too many cosmic coincidences to ignore. Stay until the end, because what you're about to hear might change the way you see our skies forever. Part 1. The Impossible Signal. Picture this. You're drifting through the emptiness of deep space, more than 3 times farther from the sun than Earth ever ventures. Out here, sunlight is weak and distant. Little more than a cold whisper. Ice remains locked in its frozen stillness. Comets go to sleep. Space becomes a silent graveyard for anything volatile. And yet, something impossible appears. A comet, not quiet, not frozen, but erupting. Pouring water into the void at a staggering rate of 40 kilograms every second. Not trickling, flooding, water streaming off a frozen world, where it shouldn't exist in vapor form at all. This is 3A Atlas, an interstellar visitor from another star's domain, a wanderer, carrying the physics of an alien system, where the rules are clearly not the same as ours. The first hints of its strangeness came from NASA's Swift Space Telescope, a mission designed to hunt down gamma-ray bursts. When Swift turned its ultraviolet sensors toward 3A Atlas in early 2025, it detected something astonishing, a glowing halo of hydroxyl molecules surrounding the comet. Hydroxyl, so what's left behind when sunlight tears water molecules apart. It's like the dying breath of vaporized ice, the last echo of water screaming as it's destroyed. So when astronomers saw vast amounts of hydroxyl around 3A Atlas, they knew one thing for certain: there was water here. A lot of it. The numbers are beyond belief. At a distance of 3.51 astronomical units from the sun, a region where comets are normally frozen and silent, 3A Atlas was spewing out water at a rate of 1. That's roughly 40 kilograms per second. The mass of a compact car vaporized into space every minute. To put that in perspective, comets from our solar system don't behave like this. Not out here. They're dormant, inert, conserving their frozen reserves until they get much closer to the sun. There simply isn't enough heat this far away to sublimate water ice directly into gas. But 3A Atlas didn't care about our expectations. You might remember Oumuamua, the first interstellar object ever detected. That visitor was completely dry, no water, no outgassing, no coma, just a silent, tumbling shard of rock slicing through our solar system and vanishing into the dark. Then came 2A Borisov, the second confirmed interstellar comet. It was active, yes, but it behaved by the book, melting, venting, and brightening exactly as expected. 3A Atlas is nothing like that. It's alive in a way that shouldn't be possible. A cry of activity in the cold reaches where silence should reign. So astronomers asked the only question that mattered: how? What could drive this kind of wild behavior so far from the sun? Could there be some unknown ice buried within it? Something that vaporizes at much lower temperatures than we thought possible? Could it still be radiating leftover heat from its birth billions of years ago? Could its rotation or orientation be focusing sunlight into hidden reservoirs of volatile materials, creating local hotspots? Or the most thrilling possibility, is there chemistry happening inside 3A Atlas that we've simply never seen before? And water isn't the only surprise. The comet is also releasing cyanide, nickel, and carbon dioxide in bizarre proportions. None of it fits any model we've ever built. Every new spectral reading adds another layer of confusion. Every fresh dataset raises new questions. This isn't just a comet behaving oddly. It's a comet that seems to operate by an entirely different rulebook. A rulebook written in another star system, under another kind of chemistry, forged under alien conditions. And now it's here, giving us a rare, front-row glimpse into how the universe might work beyond our familiar corner of space. But that realization leads to something even more unsettling. If 3A Atlas can do what our comets can't, what does that say about its birthplace? What kind of stellar nursery created this thing? What were the elemental ratios, the pressures, the temperatures, in that faraway protoplanetary disk billions of years ago? And perhaps most provocatively, is 3A Atlas just an oddball out, or is it a messenger from a galaxy of systems far stranger than we ever imagined? Every telescope capable of observing it is now locked on target. Astronomers are using everything: spectroscopy, photometry, polarimetry, every tool in the arsenal. Because 3A Atlas isn't just a curiosity, it's a window. A small fracture in our understanding of cosmic chemistry, and through that fracture, something profound might be waiting. Part 2. Nickel without iron. In our universe, comets follow patterns, reliable, repeatable patterns. When they heat up, metals start to vaporize, and when they do, iron and nickel always appear together, side by side, like inseparable companions. You see one, you see the other. That pairing has been one of astronomy's comforting constants. Until now, when the Very Large Telescope in Chile trained its spectrograph on 3A Atlas, the results defied everything we thought we knew. The spectral data lit up with strong, clear emission lines of nickel, bright and unambiguous. But iron, either missing completely, or so faint it barely registered. Nickel without iron. It's like finding smoke without fire, or footprints without feet. It simply doesn't happen in our solar system. When our comets heat enough to release metals, iron and nickel always appear in consistent ratios, because they're chemically bound together in similar minerals, formed under similar conditions, and vaporized at nearly identical temperatures. But 3A Atlas, it's breaking that cosmic rule. At around 2.8 astronomical units from the Sun, astronomers detected nickel streaming off the comet at a rate of about 5 grams per second, a constant flow second after second, with almost no trace of iron. That's not a random glitch. That's a pattern, a signature written into the comet's very composition. Several theories have been proposed, and none of them are simple. One explanation points to chemical fractionation. Maybe in the environment where 3A Atlas formed, nickel got locked into volatile compounds that vaporize easily, while iron stayed behind, trapped in tougher, refractory minerals that require much more heat to supplement. In other words, nickel might be hitching a ride with ices that release it early, while iron remains dormant. Another hypothesis involves organometallic compounds. Here on Earth, we know molecules like nickel carbonyl, where nickel atoms bond with carbon monoxide. These compounds are volatile, evaporating at surprisingly low temperatures. If 3A Atlas formed in a region rich in carbon monoxide and other organics, perhaps nickel was captured in these molecules. As sunlight warms the comet, the molecules break apart, freeing atomic nickel into the coma, while iron stays locked in the solid grains. A third possibility: space weather. For millions or even billions of years, interstellar objects drift through radiation fields, bombarded by cosmic rays and ultraviolet light. Over time, their surface chemistry mutates. Layers rich in nickel could form as radiation breaks apart and redistributes atoms, while iron gets buried or chemically altered beneath. What we might be seeing then isn't the comet's true internal makeup, but the irradiated outer skin it developed during its long, lonely voyage through interstellar space. And finally, the most thrilling hypothesis of all, 3A Atlas was born in a system with entirely different elemental ratios. Not every star shares the same chemical fingerprint. Older stars, or those formed in distant galactic regions, can have drastically different compositions, depending on what kind of supernova enriched their birth clouds. Maybe 3A Atlas originated in such a system, one where nickel was naturally more abundant relative to iron. Its strange chemistry could simply be the signature of its birthplace, an echo of a star that played by its own rules. But as always, caution is key. Extraordinary claims demand extraordinary evidence. Astronomers are still gathering data, running models, testing each possibility against reality, and so far the mystery of 3A Atlas only deepens.
Spectroscopy isn't easy. Trying to pick out faint emission lines hiding within a bright background is a challenge that pushes even the best instruments to their limits. There are detection thresholds. Faint signals can hover just below them, invisible but possibly present. Maybe iron is hiding there, just out of reach. Or perhaps its spectral signature is tangled with other overlapping features, making it impossible to isolate. There's even the chance that scientists are simply observing the wrong wavelengths altogether. As the comet moves closer to the sun and heats up, perhaps iron emissions will finally appear. That would be a relief, a sign that our understanding of cosmic chemistry still holds true. But what if it does? What if 3I Atlas completes its journey to perihelion, its closest approach to the sun, and iron never reveals itself? What if the ratio of nickel to iron remains completely inverted, defying every pattern we've ever seen across the cosmos? That would be nothing short of groundbreaking. It would mean that other planetary systems can produce comets with metallic compositions unlike anything in our own solar neighborhood, so different that our entire understanding of cometary chemistry might need rewriting from the ground up. That's why astronomers are watching 3I Atlas with such intense curiosity. Every new image, every data point, every spectral reading, it's all a test. Each spectrum is a chance to either reinforce what we think we know or tear it apart completely. And right now, 3I Atlas seems far more interested in breaking the rules than confirming them. Part 3, a comet that switches on. Normally, comets follow a predictable rhythm as they near the sun. More sunlight means more heating, which means more sublimation, frozen gases turning into vapor, which in turn releases more dust and increases brightness. The physics is simple, even boringly consistent. But 3I Atlas didn't get the memo. Observers soon noticed that this comet wasn't following the typical script. Its color began to change in ways that didn't make sense. At first, it looked fairly neutral, maybe a faint reddish hue, which is common for distant, icy bodies. But as it moved closer to the sun, something bizarre happened. The comet turned green. Not a faint tint, a vivid, unmistakable emerald glow that photographs captured in eerie detail. That striking green light came from two key sources: cyanide molecules and atomic nickel, both of which emit strongly in the green portion of the spectrum. As the comet warmed, both emissions spiked dramatically. The increase wasn't gradual or linear, it was superlinear, intensifying faster than expected from the simple physics of sunlight and distance. Here's the thing, when an object moves to half its previous distance from the sun, it receives 4 times as much sunlight per square meter, basic inverse square law. Yet, the emission lines from 3I Atlas weren't just following that rule, they were growing even faster, implying that something deeper was being triggered. A hidden process had begun, something scientists refer to as switch-on behavior. Picture this: below a certain temperature, a specific ice remains frozen and inert. Then the comet crosses a critical threshold, and suddenly that ice begins to sublimate. Gas production spikes. New spectral lines emerge. It's like flipping a cosmic switch, one moment, silent, the next alive with activity. And if enough material is available, that process can rapidly escalate on its own. What's remarkable about 3I Atlas is that it appears to have multiple switches. The first activation came from water, all the way out at about 3.5 astronomical units, much farther than expected for typical cometary water activity. Then came the green emissions from cyanide and nickel, flaring to life as the comet heated even more. Each activation hints at a different volatile reservoir being tapped, a separate chemical zone, waking up as its threshold temperature is reached. One compelling model suggests that these effects might not all originate at the comet's surface. Instead, imagine tiny icy grains being blown off the nucleus by escaping gases. These grains, now floating in the coma, remain cold for a time, but gradually warm as they drift farther from the nucleus and soak in more sunlight. Eventually, each grain reaches its own sublimation point, releasing gas from within the coma itself. This distributed source of gas could easily explain the non-linear brightness surge and the abrupt emergence of new emission lines. Another theory involves thermal fracture. Comets are fragile mixtures of rock and ice. As they heat unevenly, internal stresses build up between warm and cold regions. Eventually, something snaps. Cracks form, exposing fresh material that was once buried beneath insulating layers. Suddenly, there's new surface area venting volatile gases into space, creating what astronomers call an outburst. 3I Atlas could be cracking itself open, layer by layer, unveiling frozen chemistry from deep within. And then there are the exotic ice. Water ice sublimates at a relatively high temperature, but carbon monoxide turns to gas at much lower temperatures. Carbon dioxide sits in the middle. If 3I Atlas has a layered internal structure, different ices stacked like pages in a book, then each heating stage would unlock a new chapter of its chemistry. First, the highly volatile gases, then the more stable ones, and finally, the toughest materials near the core. This kind of staged activation isn't totally foreign. Other comets in our solar system have behaved unpredictably, erupting in sudden outbursts, brightening tenfold overnight, or even fragmenting as solar heat tears them apart. Some stay inactive until they're nearly at perihelion, before exploding with activity, but 3I Atlas isn't following any familiar timeline. It's active at distances where comets should still be asleep, and it's doing so in ways that feel almost intentional, like it's revealing its secrets on its own schedule. Now tension builds with every observation. As 3I Atlas continues its inward trek, what happens next? Will new switches trigger more unexpected emissions? Could we detect molecules never before seen in interstellar comets? Will its activity taper off, or spiral into overdrive? Every week brings fresh data and new surprises. This isn't a routine comet behaving predictably. It's a mystery unfolding in real time, a living drama written across the stars. Part 4. Where did it come from? Every object in space carries a story, written in its orbit. The path it follows reveals its past, where it originated, and what forces shaped its journey. In the case of 3I Atlas, that path tells a story stretching across billions of years and thousands of light years. Its orbit is hyperbolic, an open curve that never loops back. That means this comet didn't form here. It came from interstellar space, swept into our solar system, circled the sun once, and will soon depart forever. Its eccentricity, a measure of how stretched its orbit is greater than 1, which makes it unbound, a cosmic wanderer, free from the sun's gravitational lead. Astronomers confirmed this by tracing its path backward in time, using precovery images, older survey photos taken before anyone realized this object was extraordinary. They reconstructed its incoming trajectory. These archived images showed 3I Atlas as far back as 6.4 astronomical units from the sun, when it was still a cold, distant traveler. By linking together these faint early detections, scientists refined its orbital path with remarkable precision. The data clearly pointed outward, away from the solar system, deep into the galaxy beyond, and when combined with information from the Gaia Space Telescope, which has charted billions of stars and their movements, researchers began to narrow down the potential birthplaces of 3.
The reality is more fascinating than it first appears. The galaxy isn't random chaos. It's a structured system. Most of the stars, including our own sun, lie within a slender disc-shaped region known as the thin disk, a relatively flat plane filled with younger, metal-rich stars orbiting the galactic center in orderly paths. But that's not the whole story. Looming above and below the thin disk is the thick disk, a population of much older stars with orbits that are tilted, eccentric, and more chaotic. These stars are puffed up vertically, extending far beyond the galactic plane, and they're chemically distinct. They were born billions of years earlier, in an epoch when the galaxy contained far fewer heavy elements. Now here's the intriguing part. 3I Atlas's trajectory suggests it could have originated from that thick disk population. If that's true, this object may predate our solar system entirely. While our sun is about 4.6 billion years old, the thick disk stars can be as old as 7 billion years or more. That would mean 3I Atlas could contain ice and rock that formed before the sun even existed. Chemically, that's mind-blowing. The gas cloud that collapsed to form a thick disk star 7 billion years ago had far fewer heavy elements than the one that birthed our sun. Over time, supernovae enriched the galaxy with elements heavier than helium, the building blocks of rock, metal and light. The earliest generations of stars were almost pure hydrogen and helium, while later ones, like our Sun, contain small percentages of heavier materials. Thick disk stars sit somewhere in between. They have some heavy elements, just not as many as we do. If 3II Tellus formed in that ancient environment, its composition would reflect that lower metallicity. Less iron, less magnesium, less silicon, the elements that form planets, but still plenty of volatiles, like carbon, nitrogen, and oxygen, locked in frozen compounds. That might explain its odd chemistry. Maybe that's why 3II Tellus has such a strikingly high carbon dioxide to water ratio, or why its metal ratios look so off compared to our solar comets. It could be a chemical fossil from a time when the galaxy itself was young, a messenger from an era when the periodic table wasn't yet complete. Of course, this is incredibly hard to prove. Tracing an object's exact origin across billions of years of galactic motion is nearly impossible. Gravitational nudges from nearby stars, shifts through spiral arms, all of it scrambles the trail. But the very fact that it's plausible that 3II Tellus is older than our solar system is breathtaking. We might be observing a relic, a cosmic time capsule from the galaxy's ancient youth. If we could somehow identify the cluster where it was born, the group of stars that formed together from the same molecular cloud, we might even find its siblings, other comets, asteroids, or maybe even ejected planets scattered across the Milky Way. 3II Tellus could be just one letter in a vast interstellar message, written across the cosmos, and we're only now beginning to decipher it. Part 5. What's riding along with it? Comets aren't just chunks of ice and dust, they're cosmic cargo ships, carrying the molecular fingerprints of the environments they were born in. And 3II Tellus is transporting some remarkably strange cargo. We already know about its water output, roughly 40 kilograms per second streaming into space, even at distances where comets shouldn't be releasing any water at all. That discovery alone made astronomers sit up straight. But water is just the start.